It is time for another FFBoard project update video where I show you what has happened in the development since the last one. This time there will be a lot to talk about. We will go in depth about the development of some features here and summarize major changes since the last update video. There are a lot of new features and fixes in the firmware, the configurator got a redesign, and we even have some new hardware to show. For documenting the usage of specific features, I will make smaller dedicated videos later, as it's likely more difficult to find that in the large update videos. The first small but important change is that you can reset the emergency stop now. For push buttons, it will reset when it's clicked again, and for latching switches, if the line is held for more than 1 second, it will automatically reset when released again. Another feature we talked about in the past is a profile management system, so you could change settings depending on the game. Big thanks to Carlton in my Discord who actually implemented a system like this. So down here in the configurator we now have a profile manager. I have 2 profiles created and the flash profile. And for example, when I select the FH profile, which I made for Forza Horizon, which has a fixed steering wheel range, the range changes to 540. And the default would be 900. And with this system, I can quickly switch between settings. And this also saves all the other settings, the intensity, the Endstop, damper settings, and also effect settings. And you can, for example, for every game you have, you could make a profile. And this is pretty simple. You just open the profile manager and make a copy of a profile. So let's call this test. And then profile test is active, which is exactly the same as our flash profile now. But let's say I want to disable the CF filter and maybe make the spring a little bit stronger. Then I save this. And then when I change between the profiles, those settings would be directly loaded to the board and applied. Or also we could change the Endstop and the steering wheel range. For example, if you have a very small range for karting, for example. So we could save this and change between our 900-degree range and our 180. So in some setups you might not have the wheel directly coupled to the motor in a direct drive configuration, but instead a gearbox or belt between your wheel or joystick or any other kind of input device. And then of course your range selection and speed and acceleration measurements for the effects would not be accurate anymore. So at the moment it's set to 900 degrees. And for a configuration with a reduction, we now got the encoder reduction prescaler. So I could, for example, enter 1 to 2, which results in a prescaler of 0.5. Now all our positions are multiplied by 0.5 and we get double our range. This would be, for example, a good setting if you have a reduction with a encoder which is spinning faster than the wheel. And we could go pretty much to any fraction we can enter here. We can also go the other direction and, for example, enter 2 to 1, which results in a prescaler of 2. So all our positions are multiplied by 2 and we get half our range. And this should allow you to pretty much enter any fraction for your setup and be able to still correctly use the range selection and speed calculations with a reduced encoder, because some effects like damper, friction and inertia depend on filtered speed and acceleration values. There might be a use case where you would want to change the strength of this low-pass filtering of your speed, for example. So for this we got the advanced encoder tuning window. Here you can enter the encoder resolution. It will try to auto-detect with a biss-c encoder, so it's extremely high. But for example, when I would enter 40,000, which is a pretty normal encoder resolution for ABN encoders, then you would see a preview of the pulses coming from the encoder. So you can select the speed, 15 degrees over 5 seconds, for example. And then you can play around with encoder profiles. Low resolution would be a very smooth low-pass filter, very low frequency. Medium is kind of standard, and high resolution is a little bit less aggressive filtering, which would pass through more ripple from the encoder and might make effects also less stable, but would allow a faster response on high resolution encoders. So it really depends on your encoder and preference and system what profile you should select. You can also use the suggest profile. So at 40,000 it would suggest medium resolution. It shows you the filter frequency of the speed filter and also the acceleration filter. This UI was also made by Carlton in my community. And this actually does simulate the internal biquet filters of the firmware and shows it in a graph. When tuning effects, it can sometimes be a bit difficult to know which effects are being used in a game and which effect is responsible for what force. So we have a live effects graph, and when I enable the simple spring effect, for example, then we can see that currently one spring effect is active. A game can allocate multiple effects of the same type. This is possible. And I could also enable the damper effect. Now we can see that we have a spring effect and a damper, which would create an opposing force to the spring and, for example, dampen the oscillation. Or also the inertia effect or friction. In general, this will show you all the effects a game is currently using. And the scaling is not actually what's sent to the wheel, but the internal effects force before it's scaled. So you can see if a certain effect is clipping on its own already. And if you don't want to monitor it live, there is also the effects statistics window. At the moment, there is no effect currently active, but it will show you that these effects we have used in the last demo. So I can reset this, and when I activate the spring effect again, then we see, spring has been used. And it will also show you the maximum force, which has been seen by this effect since the last reset. So this can be useful if you have a game in the background and afterwards want to see which effects were used by this game. If the conditional effect settings sliders are not enough for you, then we also have an advanced effect tuning window now, which can show you a preview of how the force would actually look like. So, for example, with the spring effect, this is a position effect, so it depends on the position of the wheel. This line shows the position, and we can see that at this point the effect would be clipping. This is where the curve gets flat, and indeed I can really feel this in the wheel, that after this point it does not get stronger. And when I adjust the gain, I can make the curve steeper or less steep. This is basically the same thing you can also use with the spring gain slider in the normal axis tab. But here you can really see how it would behave. Same thing also, for example, for the damper effect, which depends on the speed at which the wheel turns. So when I enable the damper, you can see that it's now dampening the force generated by the spring. And here again, I can change the steepness of this curve and make the damper lighter or stronger, so it would clip at a slower or faster speed. And yeah, you can really see at which speed it would clip. And same also for the friction and inertia effect. I mean, inertia, pretty much same thing. This is friction. Friction also has a ramp up region, and you can make this slower or faster, and this also alters how it feels like. Hard to describe, but this graph is quite accurate at how the force would be depending on the speed. And with the inertia effect, this depends on the acceleration, so it will show the acceleration and yeah, make the wheel feel a bit heavier. There's also an option to use custom filters. This will enable these filter settings. I would advise you against playing around with this and sticking with the defaults. These are filters which would be applied low-pass filters after the effect has been calculated to the force this effect contributes to the total force. You can really mess up stuff with this, but it can allow you some degree of fine-tuning. Yeah, you would need to save this. And this is basically the same thing as with the sliders. So when I change the damper gain, instead of a graph, here you would see the clipping point at which speed it would be clipping. And same also for the inertia. This is basically where in the graph it would reach the maximum. I actually managed to score a batch of 10 TMC 4671 driver boards like these and 10 matching STM F407VG boards. These boards were assembled by GUI PCB, who are also today's sponsor. The small STM FFBoard can normally be made with the cheap economic service if it's black or green, and all required components are listed in their catalog for very fast and affordable assembly. If components are out of stock, you can pre-order to reserve them and use them for an assembly job in the future. Their more advanced standard assembly service allows double-sided assembly with externally sourced components with no color limitations, even on these 2-ounce copper motor driver PCBs, and allowed me to get them made in blue. Simple PCBs can be ordered for as low as $2 and now even with an aluminum substrate for better thermal dissipation. All the production files required are as usual available on my GitHub page. Now let's finish the assembly of one of these OpenFFboard TMC drivers. I pretty much just need to add the headers and a diode, because in this version we were still not able to get the LM74700, which should normally go down here. So instead we are just going to use a diode with the same footprint as the MOSFET. I'm going to take these tweezers and put them here to shield the capacitors a little bit from the hot air. Now, the next step would be to add the terminals. For the ground pin, it can help to add some hot air. And of course we have to do the same thing with this terminal as well. There were a few minor issues with the batch which were not the fault of GUI PCB, but I need to fix them until the boards are ready. Mainly I forgot to specify in the bill of materials that the pads C27 and C28 must be left blank. They were only intended for testing and will cause significant noise in the current sensing if populated with a capacitor. Also, the NTC thermistor used to measure the board's temperature was incorrectly assembled with a 10K resistor instead of the thermistor. This was actually specified in the bill of materials to be a thermistor, but might not have been clear enough in the assembly file where it was just marked as 10K. So I need to swap that part too. And last, I need to also replace the MAX 5033 DC converter that generates 5 volt from the motor supply. Back then it was unfortunately out of stock at DigiKey, so my supplier had to order them from a third party and unfortunately got scammed with non-functional fake chips. So I will just need to cut them off and hand solder the replacement I got directly from Mouser. This was also not the fault of GUI, as they were externally supplied, but a lesson to be learned here is to only buy parts from reputable sellers. So I know it sometimes can be quite difficult to keep track of new releases, especially if they have important fixes for bugs. So another new feature of the configurator is when you connect to a board, it will notify you as usual if the firmware is too old for the UI. This is because I have a new UI. But now it will also pop up an update notification if a new firmware release is available when you connect to the board. And here it's notifying me about the v1.9.6, and on the board currently installed is the 1.9.1, and on GitHub the newest release is 1.9.6. It will not show pre-releases like this release in this notification, but it will only show the actual stable releases. It will show the changelog. And then we can also the update browser, which is another window which can show you all the releases on the GitHub page. So this is basically just a release browser for GitHub. So it's showing in green our latest update, which is this one, and in yellow the pre-releases, which I have kept on GitHub to show you this. So this is a pre-release. This would not be shown as a notification pop-up. Of course, the changelog is and the release notes are also directly shown, and also the files which are attached. So we have attached the firmware file and a configurator for Mac and Windows built with PyInstaller. And you can also directly see those and click download or go directly to the release page. So this will just open your browser on the release page. And when you download the firmware, at the moment it will also just open your browser with this URL, because at the moment there is no download function or automatic flashing integrated yet. So the same thing also works for the configurator. The latest release is 1.9.7 for the configurator, and I have manually set the version to 1.9.5. So now when we start the configurator, it will also check GitHub and show an update notification that the 1.9.7 is available. And we can click on it and it will directly open a browser and lead us to the release page. So in order to update the firmware, I assume you have now already downloaded it. We go into the firmware update menu via hardware and firmware update. We switch to update mode. This will put the device into the DFU bootloader. You will need to have WinUSB installed as a driver for this device. And for the initial installation, you can also use a jumper like this and put it into the boot 0 jumper position and then reset board. This will also force it into DFU mode, the same as this button in the GUI. And in order to install the WinUSB driver, you can use a tool for it. And you might need to use list all devices and then select STM32 bootloader and manually load WinUSB. At the moment, it's already installed and it works. Or you can also use the STM32 loop programmer tool, which also automatically installs a driver with it. Careful not to install it for anything else, because this will break your device until you manually uninstall the driver from it. So now we will choose a file. This is at the moment the F407VG. So we select the F407VG firmware file and click Upload Firmware. This takes a while, but after it's done, it should reset the chip. For the initial installation, you will need to manually reset it, and then we can connect again, check the version, and we have firmware version 1.9.6 installed. Since the beginning, you were able to easily connect analog inputs like pedals directly to the internal ADCs of the FF board via the analog input pins and get a 1 kHz rate at 12 bits. But pedals are sometimes far away from the microcontroller in a high noise environment, and it can be difficult to get a clean signal even with digital or analog filtering. Another option is to mount an ADC directly next to the sensors inside the pedals and only transmit a digital signal immune to noise to the main microcontroller. A common ADC for this task is the ADS1115, which is a 16-bit 4-channel I²C ADC available on modules like this. For the moment, I have connected it to the I²C pins on the extension header of the FF board, and I have also connected this potentiometer for demonstrating it. So I have now selected the source and opened the config window, which might look a little bit different later, as I'm currently still working on it while recording this. Options for this ADC are the amount of inputs from 1 to 4 in single-ended mode and 1 or 2 in differential mode. In differential mode, channel 1 has the pin 0 as the positive and pin 1 as the negative, and channel 2 has pin 2 as the positive and pin 3 as the negative input. In single-ended mode, only half of the range is valid, because the negative is internally connected to ground, so the effective resolution is only 15 bits and the signal is automatically shifted in our firmware. So this means you will still get the full range in single-ended mode as well. When I turn on this potentiometer, you can see that the gamepad axis is moving up and down. This ADC also contains a variable gain amplifier. At the moment it is set to 2 times, but you can select it from 2/3 up to 16 times. So for example, when I set the gain to 4, we will see that the range is reduced and the gamepad value moves much faster. This could, for example, be used for load cells to switch them between a soft and strong preset together with a lower amplification preamplifier. Then we also have the sample rate setting. The sample rate is basically a trade-off between the update speed and resolution and noise. So the slower our sample rate is, the cleaner the signal, but it will take longer for an update. At the moment I am at the highest sample rate of 860 samples per second. So let me show you the sequence of operation for this ADC. On the scope, we are currently triggering on the sample read command, which comes at the end of the chain. So our trigger frequency is also the update frequency of the single selected pin. Because it can only sample from one pin at a time, when starting a conversion, the multiplexer is set first to a specific input, in this case pin 1. When the conversion is started, it will take some time depending on the sample rate. At the highest rate, it will still take more than 1 millisecond, so we will periodically ask the ADC every millisecond if it's done yet. Let me show it to you on the scope. So this is the command where the sampling is started. Then we will ask the first time if it's done yet. It is not done yet. It will wait a bit. So in this case, it might already be done, but it seems like it is not. And the third time, it's probably finished somewhere in between the previous and this polling. And now it is done, and it will then start reading the sample again. And the chain begins from the beginning if we have another pin, for example, to sample, or we just sample the same pin again when we only have one input selected. During the time of the slow I²C transfers and the wait time until the sampling is done, the chip can fortunately do other tasks because we are using interrupt-based transfers and do the polling in a thread. When it's done with sampling and the sample is read, it will be stored in the output buffer, which is then sent to the PC every millisecond. So, for example, when we select a slower sample rate, at the moment we are at 860, but when we, for example, select just 16, so at 16 samples per second, we would expect an update rate of about 16 Hz. And indeed, when we look on the scope, our trigger rate is about 15.6 Hz. So this is just pretty slow, so I would recommend you using at least 128 samples per second, which is the default. So on the topic of analog inputs, let's take a look at a pretty often requested feature. I got a FFBoard here with the ADS1115 and a Logitech shifter connected to the analog inputs pin number 5 and 6. So we open the A-in pins. I have disabled all the other not important channels because they will just read noise. And we can see, yeah, there is something new. There is a range slider, so when I move it to the right, we see it does not cover the full range. So it only goes from 25 to 80%. And we can use this range slider to select a smaller range. And now it will correctly clip to 0 and 100% on the edges. And yeah, the same thing. In the gamepad output, we see it covers the full range. The vertical axis already covers pretty much the whole range, so this is fine already. And we can also use auto ranging still, and it will first reset the limits and build up the range while it's being used. When we are happy and we don't want it to happen the next time, then we can disable auto ranging again, and the calibrated limits will stick and be saved when we close this and save to flash. Another feature is also a low pass filter. If you got a very noisy signal with pedals and don't want to build analog filters, which would be better, you can enable a digital low pass filter instead, which does make the signal a little bit cleaner, but would introduce a slight delay. The same thing also works with the ADS1115, the ADC I've already shown. I have selected one input, but we could also go up to all four. And now we get 4 range sliders and 4 output values. And yeah, same thing here. We can select a range, smaller range or a larger range, depending on our inputs. At the moment, these are just open, so they will read just whatever intermediate value is currently present in the ADC. Auto ranging, of course, also works, and a low pass filter is also possible, which is not really required with this ADC because it's already pretty clean, but it's possible. And yeah, when we increase the sample rate, then we can see that there is a little bit of noise, and when we enable the low pass filter, this is slightly reduced. You can also select the I²C rate. So in this case, I have selected 400K. Standard is 100. I would recommend using 400 for this ADC because there's quite a lot of data to be sent. So let's take a look at something slightly different. This is a BMW E87 instrument. And the nice thing is these are very inexpensive. You can really get them for cheap. And they can be controlled via a CAN bus. They just need 12 volts on the lower 2 pins. And a CAN high, CAN low and ground connection. These are connected to this FFBoard. CAN high, CAN low, ground, and the CAN termination resistor must be disabled with this. If it's enabled, set, then it will not work. But yeah, with this setup, we could now send data to this cluster. I have set the OpenFF board into the SavvyCAN mode and prepared a frame. This frame, the first one, will enable it. This just tells it to wake up and that the engine is on. So when I send this, every 100 milliseconds, you see it has turned on. And then we got the second one. This is controlling the motor RPM. And when I enable this, I have also enabled another rule which increments a value. So you will see that it will slowly rise and then reset. And then we also got this one, which is controlling the fuel level. And this will slowly go down. There's a very high delay inside this dash, so it will move very slowly, and I'm just sending one frame every 1500 milliseconds. And yeah, you can also control all the lights and blinkers. So now this OpenFF board is in normal force feedback wheel mode, and you can control the CAN port via HID as well in this mode, while you are in game, for example. For that I have written a little Python script, and when I run this, you can see that the dash turns on, the lights come on, it is controlling the indicators, and also the backlight is currently active. And yeah, you could, of course, control all the aspects of these instruments, for example, from a simhub plugin while you are in-game. Of course, massive thanks to my supporters on Patreon, JLC for making my boards, and all the users giving feedback in our Discord community. Check out the links in the description if you want to get more information about this project.